Hello everyone. Before we discuss the cooling system, let's first understand what an HPGE detector is. HPGE, which stands for High Purity Germanium Detectors, is a radiation detector commonly used to detect and measure gamma rays. It is widely used because it provides very accurate and high resolution measurement. However, HPGE detectors cannot operate effectively at room temperature, because when the temperature is too high, thermal noise is generated inside the detector, which affect the accuracy of the measurement. To solve this problem, a liquid nitrogen cooling system is used. Liquid nitrogen has an extremely low temperature of about -196 degrees Celsius, which help keep the detector a very low and stable temperature. By cooling the detector, thermal noise is reduced and allowing the HPGE detector to achieve better sensitivity, higher energy resolution, and more accurate result. This is why liquid nitrogen cooling is an essential part of HPGE detector system that used in research, radiation monitoring, and other scientific applications.
Therefore, to explore this integration of liquid nitrogen cooling for HPGE detector, there are three main objectives that we aim to achieve. First of all is practical laboratory exposure. This objective is to gain the direct insight into the professional research environment so we can observe firsthand how these highly sensitive HPGE systems are operated and maintained. Second, cryogenic in application. This is to help us truly understand the practical handling, safety measure, and transfer processes of liquid nitrogen that are essential to keep the detector at its optimal operating temperature. And lastly, bridging the theory and practice. This final objective serves to connect our classroom physics concepts such as thermal noise reduction and heat transfer with actual real-world laboratory execution.
The cryogenic technology used in HPGE detector is liquid nitrogen cooling. This technology is essential because HPGE detector cannot achieve their high energy resolution at room temperature. At higher temperature, the thermal energy generates excess charge carrier in the germanium crystal, which increases leakage current and electronic noise. To overcome this problem, the detector is cooled to approximately 77 Kelvin or minus 196 degrees Celsius using liquid nitrogen. The liquid nitrogen is stored in a Dewar flask which provide excellent thermal insulation. The cooling is then transferred to the HPGE crystal through the highly conductive component called a cool finger. By maintaining the crystal at cryogenic temperature, thermal excitation is significantly reduced, resulting in lower noise level, improved signal-to-noise ratio, and much better energy resolution. Therefore, cryogenic cooling is critical technology that enables HPGE detector to perform precisely in gamma ray spectroscopy.
The slide shows the main physics concepts involved in the liquid nitrogen cooling system of an HPGE detector. First, heat transfer occurs by conduction. Heat from the HPGE crystals is transferred through the cold finger to the liquid nitrogen reservoir. Since heat naturally flows from a higher temperature region to a lower temperature region, this helps maintain the detector at cryogenic temperatures. Next, cooling the detector to 77 Kelvin suppresses the thermal excitation. At high temperatures, thermal energy can generate unwanted electron-hole pairs inside the germanium crystal. By reducing the temperature, these unwanted charge carriers are minimized. Another important concept is the latent heat of vaporization. Liquid nitrogen absorbs heat from the detector and evaporates. This phase change continuously removes thermal energy while keeping the temperature nearly constant. As a result of the low temperature, electronic noise and leakage current are significantly reduced. This produces cleaner electrical signals and improves the detector's performance. Finally, the reduction in noise leads to improved sharper gamma ray peaks, allowing more accurate identification and analysis of radionuclides. Therefore, liquid nitrogen cooling is essential for achieving the high sensitivity and excellent energy resolution of HPGE detectors.
Now, the safety aspect of handling liquid nitrogen. The first hazard is frostbite. Direct contact with liquid nitrogen can freeze skin and body tissue almost instantly, that causing serious injuries. The second hazard is oxygen deficiency. When liquid nitrogen evaporates, it turns into nitrogen gas. In a poorly ventilated area, the nitrogen gas can displace oxygen in the air, which increasing the risk of suffocation. To reduce this risk, several safety measures must be followed. First, appropriate personal protective equipment, or we call it as PPE. So this includes cryogenic gloves, safety goggles, and closed-toe shoes. Second, liquid nitrogen should be handled carefully using suitable equipment and procedures. Direct contact should always be avoided. Several engineering controls are also used to improve the safety. One example is the Dewa flask, which is specially designed with vacuum insulation to minimize heat transfer and to reduce liquid nitrogen evaporation. Another example is the Mobius active cooling system that we observed during the industrial visit. So this system uses electricity to recondense nitrogen gas back into liquid form, reducing nitrogen loss and extending the storage time.
So, in conclusion, this visit site provides us with insight into the application of cryogenic technology in scientific research and radiation detection. We learned the HPGE detection required liquid nitrogen cooling at 77 Kelvin and to minimize thermal noise and leakage current, allowing the detector to achieve excellent energy resolution and accurate gamma measurement. Through this visit, we also gained a better understanding of important physics concepts such as heat transfer, thermal excitation suppression, latent heat of evaporation, and electronic noise reduction. In addition, we observed the importance of safety practice and engineering control when handling cryogenic liquids such as liquid nitrogen. Overall, this experience successfully connected the theoretical concept learned in class with practical industry and research application, enhance our knowledge of low temperature physics and superconductivity.